Hey guys, we're going to go into waves a little bit further. You got introduced to it late last week, so I'm going to bring up a slideshow and eventually introduce some equations on this stuff. This slideshow will also be posted within the assignment for you to access, and we'll be using it throughout this week and probably in the next. And some of this will be a little bit of a review to the wave stuff I did last week. So, the idea of waves, number one thing is that all waves have one purpose, and that transfer energy in some sort of way. I mean, even as like an ocean wave that we're all familiar with, it transfers energy. There's a couple different ways to classify waves. First, we could classify them in the categories such as if they need a medium to travel on or if they don't. A medium just means stuff, actual matter. So mechanical waves need a medium. They need stuff. They can't go through space, in other words. So ocean waves are an example of that. If you put a wave on a string, the string is the medium. There's actual stuff involved that the wave is traveling on, which we call a medium. It's a mechanical wave. If it doesn't need a medium, it's electromagnetic. You go through space, you go through a vacuum. That doesn't mean it can't have one a medium. It just means it doesn't have to. This is just a quick picture of the electromagnetic spectrum, which we'll talk more about another time. But you've probably heard or in other science classes learned about some of these waves. There's 7 general categories, ranging from weak energy radio waves to high energy gamma rays. But the point right now is that all these waves in this category are electromagnetic, and they do not need medium to travel on. That's just another different picture of one. All right, another way to classify waves is basically like the shape they make or the path they travel. The probably most popular one that we're going to study the most is a transverse wave pattern. And here's several parts you need to get familiar with on a transverse wave. Imagine this is just a snapshot or a freezing of a wave, a pausing of it, because in reality it would keep moving and traveling. So the first most important part would be the wavelength of a wave. And actually that symbol right there, it looks like an upside down Y, is called lambda, the Greek symbol lambda, and it represents wavelength. Wavelength is defined as the distance between any 2 repeating points. And although we could pick any 2 repeating points, we usually pick some nice repeating points, like what's called crests. Crests are the high points. Here, here, and here are crests. So if we go from one crest to the very next crest, that's considered the wavelength of the wave, and it is a length. We typically measure it in meters or some other prefix type of meter. Also, another important point is the bottom of the wave, and these points are called troughs. So like the opposites of crests, these points down here are the low points. Another measurement we can make is from a crest to the mid position or a trough to the mid position. That would be known as the amplitude of the wave. And finally, this line is technically just an imaginary line. We call it the equilibrium position. So if the wave stopped or rest, it would be right cut through the middle of a crest and a trough. Imagine if we were making a wave like this, a mechanical wave, like by swinging a rope up and down with our arm. Well, when we're done swinging, it would return to its rest position. That would be the same as the equilibrium position. The second type of wave is known as a longitudinal wave. It goes side to side. We usually don't imagine this type of pattern until we study waves. Some waves don't travel up and down through crests and troughs. Some travel side to side. Imagine a spring like a slinky, and and you vibrating it side to side would be a good example of this. Some areas of that sync would be compressed, so we call those compressions, like right here. Some areas would be stretched, their maximum stretch for that situation. And this is kind of a weird word, but it's called a rarefaction. Compressions and rarefactions are essentially the crests and troughs of a longitudinal wave. They have wavelengths. If we took any two repeating points, like a compression here to the next compression, that would be the wavelength of a longitudinal wave. The direction of travel is still horizontal, but the movement of the molecules are side to side. This says movement of air molecules, and that's because this particular diagram is trying to represent sound waves. Sound waves are actually longitudinal. We'll learn more about those at a later time. They're both mechanical and longitudinal. So in the end, the two general ways to categorize waves are: one, are they mechanical or electromagnetic, and two, are they transverse or longitudinal. I'm not going to say much about this one. It's not often considered a category in itself. It's kind of a combo of the two, transverse and longitudinal, surface waves. In a surface wave, the very top of the wave is transverse, but under the material at the top, it might move side to side and be longitudinal. Actually, the water in an ocean is like this, where the top you would bob up and down, but if you ever got like sucked underneath an ocean wave, you go side to side. Also, like the ground during an earthquake is something like that. But we're not going to really say much more about that. We're just going to primarily focus on transverse waves and a little bit with longitudinal waves. All right, now some just wave terminology we should know. A wave pulse is known as a single disturbance in a medium, and a traveling wave results from periodic motion. I'm going to switch screens real quick here and show this motion. There's a better way to check out. Okay, so in this simulation, if I just put one disturbance on this, let's say rope, that's a pulse. Notice one quick disturbance, it didn't keep going. But if I oscillate it, that's now a traveling wave. You can see the what's putting the energy into the wave. And remember, always transfer energy. It's continual and periodic. Back to the notes. There's just another wave screen. We looked at that already. Here's just an explanation in words of those parts we already went over. I'm just going to go past that. Now math, which really the equations are very short and simple. You just got to understand what they all mean. All right. There's some features of a wave that we can't just freeze and point to, because they're properties of the movement of the wave. Frequency, and big T represents time period of the wave. V means the velocity of the wave, and of course that symbol that looks like the upside down Y, which is a lambda, is the wavelength. So let's describe first for everybody what frequency is here. Now, the definition says number of vibrations per second at any one point on a wave, and it's measured in something called hertz. So let's look at this on a simulation, and I'll play this again. Now, before I hit play, I'm going to put my cursor here, my arrow, like at a nice point of the wave, like maybe right here on this crest. And we would count how many waves, crest to crest, let's say, because they're nice features, pass in 1 second. that would be the frequency of the wave. So if I would count starting now, 1, 2, 3, 4, and pause it. If 4 full disturbances or full cycles or 4 vibrations, you could say it anyway, pass in 1 second, that would mean that this wave has a frequency of 4 vibrations per second. 4 cycles per second would mean the same thing. Now, I didn't actually time it there. It would be a little tricky on the simulations to do that, so I just said pretend that was 1 second. But actually, if you look down here on this wave, the frequency is 1.5 hertz. So that must mean in reality 1.5 full cycles complete every second, every full second. So as this wave goes, let me change the frequency. Watch what happens as I up frequency. It becomes more frequent. We see more crests and troughs occurring, right? Most I could crank it up to is 3 hertz. That means 3 cycles per second. That means in 1 second, if I put a predetermined spot that I focus on, like my arrow cursor up there, that means in 1 second, 3 crests or 3 troughs are passing that point in a second. 3 complete cycles per second. If I crank it down to something lower, look at the wave. Now we're at 1/2 per second. In 1 second, we don't make it through a whole cycle. We only get halfway to the next crest. So that's simply what frequency means. And something just kind of important to point out. Notice that when I change the frequency, it has no effect on the amplitude. The amplitude, remember the distance from the rest line, this dashed horizontal line to crest or trough remains the same. So frequency and amplitude are completely independent of one another. I can change frequency all over the place. That doesn't affect the amplitude. So that's the deal with frequency, and the units we use are known as hertz. And hertz represents, as an abbreviation for it, cycles per second. So if I would say 10 hertz is the frequency of a wave, that would mean it's going through 10 full cycles in 1 second. Now this equation says that frequency equals, this is straight up inverse anytime we put 1 over something. Frequency equals 1 over the time period. The time period is very similar to frequency. However, let's go back to the simulation. However, it's the time required for just 1 cycle. Now that's not shown on the sliders down here. So let me put my cursor up here. I'll slow it down to make it more noticeable. Okay, so looking where my cursor is, let's say I actually do have a timer right here. If I start my timer, I'm going to put my cursor here and count how long it takes to go through just 1 cycle. I'm going to have to slow it down if we're going to do this anywhere near accurately. Okay, this is a pretty low frequency wave, so it should be possible for me to do it here. I'll crank it up a little bit so we can see it better. Okay, right here. It looks like it doesn't work out because it moves my cursor. Let me just explain it. I can't fully do it on this one. But if I would be able to time how long it just takes for 1 cycle, 1 crest to crest, that's the time period. Remember that sounds a little bit like frequency, and they're closely related, but it's not the same thing. Frequency is how many full cycles occur in 1 second. Time period is how long it takes for just 1 cycle. And in a way, they're opposites with one another, and that's why they're mathematical inverses. So if we know one, you could find the other. If you know the frequency, you could find time period and vice versa, because they're the only 2 unknowns in that formula. Time period is a time, so it's just simply in seconds. All right, 2 other equations we have are this is kind of known right here as the wave equation. The velocity of the wave equals frequency times wavelength. And if we sub this formula into this one, we could get also that the velocity equals the wavelength